Hi everyone, my name is Yueqi and I'm happy to be here to introduce to you the branch predictors and some static ways to do the prediction. Branch predictors are useful when we are using speculant squash to solve the control hazard in pipelining. Say that if we meet a BEQ instruction in our program, we first load it and then we move on to the decode stage. When the BEQ instruction is in the decode stage, in pipelining, we try to load a subsequent instruction. And here we meet two choices. We can either load the instructions that correspond to PC plus 1, or we are loading the instructions that correspond to PC plus the offset. In other words, we are trying to predict whether the branch will be taken or not. The reason why we are predicting is because before the BEQ is getting into the execution stage, we don't know if the branch will be taken or not, but we still need to load the instruction before that. So that's why we are predicting. There are many ways to do that, static ways or dynamic ways. Because the time's sake, we won't get into the dynamic ways. For static ways, the first one is always not taken, which means that when our BEQ instruction is in the decode stage, we always predict the branch will not be taken. So we load the instructions that correspond to PC plus 1. This is a very simple algorithm, but will give us a very high miss rate. So we want to find better ways to do the prediction. The second prediction algorithm will be always taken, which is the reverse of the first one. When the BEQ is in the decode stage, we try to always predict the branch will be taken. So we load the instructions that correspond to PC plus the offset. But here, we meet a very critical problem. How are we going to know the offset before we get into the execution stage? And the answer for that is there's no way to do that. In fact, if we are only executing that BEQ instruction once throughout our program, there's no way we can know the target of that BEQ instruction before getting into the execution stage. So we can't predict that to be taken. But luckily, from statistics, we see that usually BEQ instructions are run multiple times. This happens in a for loop, for example. We check whether I is smaller than some number, and that BEQ instruction will be executed multiple times through our program. So if we are executing that multiple times, we want to store the target, the offset, in some table so that in the second time or the third time we're executing that BEQ instruction, we know what the offset is. That will enable us to predict that branch to be taken. And that's why we use a branch target buffer. We can understand this as either a dictionary or like a hash map. We have a key that is PC and the value that is offset. If our BEQ instruction is in the address 100, we store this 100 in the PC and store the offset in the offset state. So when the second time and third time we're running that BEQ instruction, we check the instruction address. If that equals to 100, we know the offset, and we can then predict the branch to be taken. So this branch target buffer enables us to predict the branch to be taken. The third algorithm is backwards taken, forwards not taken, which means that if the BEQ instruction is pointing forwards into the program, we predict that to be not taken. If it's pointing backwards, we predict that to be taken. That seems kind of random, but we can use the for loop example again. So in the for loop, at the top of the loop, in every iteration, we check whether I is smaller than some number. And for that instruction, we are pointing forward. So we predict that to be not taken always. But at the end of the loop, we always have a BEQ 00 start, which points us back to the loop to check the condition again. And that instruction is pointing backwards. And because it's checking 0 and 0, we know that it will always be evaluated as true. So that's why we use branch backwards always taken. So comparing those three algorithms for the static methods, we notice that the backwards taken, forwards not taken, will give us the lowest miss rate. That's my introduction on branch predictors and some static ways to do it. Thank you.